Yeah, I feel like you choose your difficulty. Right now for the HSC, everyone has to kind of work hard. Once you get to university and after university, you choose the difficulty level you want to play life at. And you can choose to play games or careers which are high income and less challenging. And you can also choose some careers that are higher income and a lot more challenging as well. Just to give you an example, with medicine, you can be a GP, be very comfortable financially, have a good work-life balance, and enjoy time with your patients. Or you can try to get into surgery, which is incrementally barely more paid from that point of view, but you work so many more hours. For example, in my case, with my master's degree right now, that's about 20 to 30 hours of additional study in a week, on top of work, which is currently about 7 a.m. sometimes to 8 p.m. It's fun. I love it. But you choose your difficulty. Just make sure with whatever career you're picking, you're kind of ready for the lifestyle that it will also accompany. Let me know if you can all see my screen. We'll jump into.
Wait, what? Sorry, just what specialty are you doing for your master's degree?
So the master's is just a master's of surgery, and you can pick certain subjects or elective topics that lean towards one surgery or another. With me personally, I'm not too sure which surgery I want to do because there's a lot to consider. Even with things like general surgery, which is more abdominal surgeries, you have to consider the lifestyle, in which case for general surgery, it's a lot of acute presentation. There's a lot of patients who have life-threatening problems, which will call you or require you to come into work middle of the night or 2 a.m., even when you're working as a boss, right? Whereas there are other specialties like ear, nose, throat surgery, where once you become a consultant surgeon, there's not too many emergency cases that will bring you up in the middle of the night. You have to think about, you'll be training for 10, 15 years, but the majority of your life will be as a boss if you do get in that specialty. You want to ask yourself, do you value family time? How much family time do you value? And are you fine with emergencies and having disrupted schedule? Do you love living at the hospital, etc.? So that's kind of the decision I'm trying to make now with my life. Good. All right. So right now we spoke about different acid-base pH titration curves. So this lesson is all going to be about pH titration curves, conductometric curves, and buffers. And the goal is we should finish Module 6 today. Okay, Module 7 is exciting. It's a whole different way to think about chemistry. So you learn how to name things from scratch. And you learn that it's theoretically possible to make any organic compound you want based on your understanding of chem. So let's get there. Titration curves, how do we create a titration curve? So a curve like this, right? How is it made? Ethan?
Whilst doing the experiment, you kind of put the pH probe inside the conical flask, and like every 1 mil or 2 mil, you measure the change in like pH.
Yeah, good. So again, titration is that stoichiometric reaction between an acid and base. You're trying to determine the concentration of an acid or base. Whenever you're reading these pH titration curves, the first most important thing to do is orient yourself, right? So I liked how Ethan straight away said pH probe is in the conical flask. Sid, who's in the conical flask and who's in the burette in this graph?
So the base is in the conical flask and acids in the burette.
Very good. And how do you know that?
At the start of the thing, when the zero volume added, it's at a pH above 7.
Good,
So
right?
base.
So the solution in there is the base. Good. You can confirm it because volume of acid added, that's a variable amount. It's going from 0 to 160. The only piece of glassware that delivers a variable volume of solution is the burette because it has that stopcock that turns and delivers drops of acid. So we can say base is here, acid is here, right? First thing we note, how do we determine the strength of the base, right? we can see initially at our starting point in our pH titration curve, are we starting very high, close to 14, or are we starting pretty low? Sid?
I'd say it's pretty high.
Okay, sure. All right. So Sid's saying we're starting pretty high. So what does that tell you about the strength of the acid and base? And again, I'll make this caveat, everyone. pH only tells you concentration. It tells you the concentration of hydronium ions present in the solution. Okay? Strength is all about degree of ionization. But here, we're just making an educated guess based off the pH as to what the strength of the acid is. There's actually no clear link between pH and strength. So, Akshita, onto you. Sid said we're starting high, but for me, high is between 12 and 14, right? I'd say we're starting pretty low, but let's just say you go with what Sid mentioned, which is also reasonable. We're starting pretty high. Akshita, what does that tell you about the strength of the acid or base? Akshita, we're starting pretty high, pH greater than 7, so we know it's a base here. What can you tell me about the strength of the base based on how high the pH is?
It's relatively high as well.
Yeah, so what does that tell you about the strength of the base? That's my question.
Whether it's strong or weak is that, yeah, so strong if it's high.
Why is that?
Because there's more hydroxide ions.
Okay, yeah, so you can say it's most likely a strong base if it's starting high, because a strong base will have 100% degree of ionization, meaning 100% of the base molecules BOH will dissociate to form B plus and OH minus. So it's going to release a lot of hydroxide ions, and that should that should increase the pH, right? So starting high means strong base. If we started low, it would be a weaker base, right? That's the guess we're making so far. We could be wrong. Going to Ethan, the end of this graph, is that at a low pH, pH of 1, or is that high?
Very low.
Yeah, it's pretty low, right? So we're ending low. So what is that telling you about the acid? Because we know at this point there's only acid or an excess amount of acid here, because first of all, the pH is less than 7. But what can this tell you about the strength of the acid, Ethan? Strong or weak acid if it ends low?
Strong acid.
Strong, right? So the reason for that is if it's a strong acid, it's going to have 100% degree of ionization, which means it's going to release a lot of hydronium ions. Every single bit of BH will ionize to form B minus and H plus. Okay, so we get 100% degree of ionization. That should drop the pH very low. That's my educated guess, right? So far, everyone, we think this is a strong base, strong acid titration. But this is where you're going to find your challenge. Rithanya, where would you expect equivalence points? Equivalence point, Rithanya, could you define it for us and tell me, where would you expect the equivalence point to be for a strong acid, strong base titration?
Well, the strong acid, strong base should be around 7.
Should be at 7. And can you explain to the class why it should be up here at 7 and not down here where it is at 5?
I think because, yeah, you need to know the difference between the dip and then you find the middle. But then I think that the base should be a weak base.
Good, but first of all, explain to us why a strong acid, strong base would make a neutral. Oh, I already explained it to us. When you have a strong acid, strong base titration, well, what's the conjugate of a strong acid? It's an extremely weak base. or a neutral base. What's the conjugate of a strong base? A neutral acid. So the salt that we make, everyone, is going to be neutral. The conjugate of a strong is neutral. Conjugate of a strong acid and a strong base is going to be neutral, right? So salt should be neutral. Remember, equivalence point is a point where there's no more acid and base left. All the acid and base have exactly reacted and only made salt and water. So the pH at equivalence point is always only dependent on the pH of the salt. Since we make a neutral salt and a strong acid, strong base, it should always be at pH 7. The pH is not 7. So what is this telling us? Let's go back to Sid. Sid, what is it telling you about the salt? Sid, is it an acidic salt or a basic salt at equivalence point?
It's saying it's an acidic salt.
Good. So from this titration, we've actually made an acidic salt, right? And remember, it's always weakly acidic. So what's the conjugate of a weak acid, Sid?
Weak base.
Good. So straight away, we know the base here must have been weak. Did everyone see what we just did, everyone? So since the pH wasn't 7, the pH was less than 7, we went, okay, this must be a weakly acidic salt, right? And the conjugate of a weak acid is a weak base. So we straight away know that the base was weak. What about the acid? Well, the acid must have been strong, because what's the conjugate of a strong acid? It's an extremely weak or neutral base. Okay, and so that's why it's not contributing anything to this end of the salt. So this is a weak base strong acid titration. Now, that's why it's so important after you've guessed the strength of the acid and base to look at the equivalence point and determine if it makes sense or satisfies your hypothesis. This is the most important point, looking at the equivalence point. Okay, there is another feature in this graph that is cueing you in to understand that this is a weak base titration. Does anyone know there's another part of this graph which is clearly showing you the base must be weak? I want you guys to all think about that. Well, Mohammed, question?
I just have a question about the equivalence point. Is it the middle of the base and the acid? Is that how you get the equivalence point?
Yeah, good question. The equivalence point, Mohammed, is you get it by, it's kind of like maths. You look at the vertical drop, right? So the vertical drop starts about here in the graph and it ends about there, right? You then draw a line with your ruler and you find the halfway point. So it needs to be equidistant.
Okay.
Either
So
side
the
of that
drop,
vertical.
the two drops.
Yes.
Okay.
It's technically the single drop, right? So you just get that line. I would get a ruler like this. I'd draw it and say, okay, the drop ends about there, starts about there. The midway point is around right there. And that's your equivalence point. Halfway down that vertical drop of the graph. Good question. All right, so can anyone tell me what's the other part of this graph that is telling you that the base is weak? Have a look at your notes. Don't look at the words. Have a look at the other graphs that we've gone through, everyone, in your notes, and tell me what is different in this graph. I don't want to spoon feed us. This is where you have to critically look and see. Ethan, what is it?
Is it like the first, I'll say 5-10 mils when you add like acid?
Good. It's this region and this region, that flick, right? Have a look at a strong base, strong acid titration. Let me show you again so you can all appreciate it, right? Strong acid, strong base titration, silic acid. Here, let me rub out all the mess that I made from the last lesson. Have a look at the graph. Do you see that little wink, that little eyelash, that little flicker? You don't see that. You go straight from here down. Whereas here in this graph, you can all see that little flicker. Can you see where this section where it drops down rapidly and then it tries to maintain pH all throughout here? This is called the buffer region of the graph. Specifically, because they're going to ask in your exams, label the buffer region. The buffer region is not this drop. That's a sudden sharp drop in the pH. This is the buffer region. Remember, what is a buffer? It's a solution that's resisting changes in pH. Have a look at this. The base, even from about, I'm guessing this is about 10 ml, all the way up to about 70 ml, maintains a pH of 9, even though we've added 60 ml more of acid. It's behaving as a buffer. This is the buffer region. You will always see a buffer region when either the acid or the base is weak, right? Does anyone want to explain why we have this buffer region? I'm going to give you all a couple of moments to think about it. Why is there a buffer region forming? Why do we think there's a buffer region? Ruthania, do you want to try give me an explanation? Why do we have a buffer region in this weak base strong acid titration? And to help you out, if you're stuck, use an example of a weak base, use an example of strong acid, write the reaction, and you can explain it. Ruthania, can you explain why there's a buffer region? Any ideas? I wrote this reaction to help you out. It's all right. I'll move to Akshita. Can you explain the buffer region?
Is it because it's not like it doesn't completely ionize, and because of that complete ionization, it kind of there's like a region where because it's not an equilibrium reaction, the region is there kind of.
Sort of. So maybe I'll just use acetic acid as an example, right? Imagine we've got the acetate ion, CH3COO minus plus HCl gives us CH3COOH plus, we just do it like this. I'm just trying to write a reaction that makes sense to all of us. Okay, we'll just use this for now. Okay, so this is a reaction between, say, sodium acetate and hydrochloric acid. Remember, with the base, we don't like to use the metal ion when we're doing Bronsted-Lowry equations. So what's going to happen is initially when we add our HCl acid, that's going to react, and it's going to first of all sharply decrease the pH because HCl has been introduced into the solution of base. But what happens is when we add HCl, we form the conjugate acid of our weak base. And what ends up happening is a similar amount of any weak base and a conjugate acid form what's called a buffer, right? We can write the equation for a buffer, right? It's going to be CH3COOH plus H2O gives us H3O plus and CH3COO minus. this buffer forms from this point in time, and it will act until this point in time. Now, Sid, what will happen when I add even more acid and I increase the hydronium ion concentration in the solution?
The reverse reaction. So the system will want to decrease the amount of hydronium, and so the reverse reaction is favored.
Good, according to Le Chatelier's principle. So now what's happening here, everyone, is even though we're adding more hydronium ions, the reverse reaction is being favored. And that's partially decreasing the hydronium ions and therefore minimizing a drop in pH. Do you all see the pH is still slightly dropping from here to here to here, very slightly, right? It's not staying the exact same constant, but it's being minimized. Now, can anyone tell me what happens at this point in time which causes such a sharp drop in pH? What has happened to the buffer? Bethania, I'm going to come back to you. This is your buffer here. It's been shifting to the left more and more and more. What happens that disrupts the buffer and completely stops it working after this volume right here?
It's reached like buffer capacity, so like it stops resisting pH.
Well, what do we mean by it's reached its capacity? Think about it. One of these ions is no longer present because the buffer has shifted so much to the left. Think about it. The definition of a buffer is when you have similar amounts of a weak acid and a conjugate base. Which one of those two ions, Rithania, completely disappears at that point in time due to the equilibrium shifting more and more to the left? Which ion would disappear?
Hydronium ions?
Not hydronium, because when you think about this, acid is always being acid, so added. So hydronium is not disappearing. So you need to understand Le Chatelier's principle. We're adding acid, which is going to increase hydronium. Le Chatelier's principle slightly decreases the hydronium, but there's still always going to be some hydronium increase. That's why the pH keeps dropping from here to here to here. What's the only other ion on the right-hand side of this equilibrium, Rithania, which is going to be completely depleted?
Acetate.
Acetate. So the reason that the buffering region stops after about this point in time, or this volume of acid being added, is because now the equilibrium shifted so much to the left, there is no more acetate. Acetate ion has been completely exhausted. Okay, and so the buffer has broken down, and that's when you get that complete reaction. Very good. Good. So key points, I'm going to rub all this out and just show you, I'm going to show everyone how to think about these graphs one time, only because this explanation was quite long and winded because I let you guys take the reins. If I was a student and I saw this graph and they asked me to determine the strength of the acid and base, which they always ask the same question, this is exactly how I'd break it down. I would go, okay, we're starting at about 10.5, which is a low start. Okay, now first of all, I need to draw and orient myself. So this is what it looks like. Burette, conical flask. And since I'm starting at a basic pH, and the pH probe isn't always in the conical flask, since I'm starting at a basic pH of 10.5, my base is in my conical flask, and my acid is being added in my burette. And that makes sense because the volume of acid added is a variable amount. We start low, which means it's probably a weak base, because weak bases have less than 100% degree of ionization, and that's not going to increase the pH as much as a strong base would, right? The next thing I do is I look at the end of the graph. We end very low. We end at pH of 1, which is so close to 0. That tells me it's probably a strong acid. Now I go, okay, well, I'm assuming this is a weak base, strong acid titration. What kind of salt should it make? And my rationale is a strong acid will make a negligibly weak conjugate ion, so I don't care about it. A weak base would make a weak acid conjugate ion. And that weak acid conjugate ion would make the salt weakly acidic. Is the pH in the weakly acidic range? Yes. Final thing I want to confirm, I said that there was a weak base up here, so there must also be a buffer region wherever that weak acid or base is. Do I see a buffer region? Yes, I'm 100% right. That is how I want you guys to systematically break down a pH titration curve question. Good. What's the final question they like to ask, Ethan? Sometimes in trials, they won't always ask this they will not ask this in the HSC, but what should you memorize as well at the very end?
Wait, sorry, what's your question?
What else should we memorize? And the answer was, what indicator should you use for this titration?
Oh,
Has anyone learnt these graphs and know what indicator we use for a weak base strong acid titration? Sid?
Would it be methyl orange or red?
Very good, right? And Sid, how did you know that? Did you learn it at school or did you read this yourself in the notes?
I just learnt it myself.
There you go, right? That's literally what everyone should be doing here. Don't wait for me to teach it to you in class, right? If you learn it yourself, read it yourself, understand it, by the time I teach it to you in class, all your questions will be fine-tuned towards the difficult stuff. And you won't be thinking really hard and trying to absorb the basics while the information's coming at you, right? All of you, I expected you all to have read these notes up to buffers, okay? It's good. Good job, Sid. So with the indicators, the indicator we want to use is methyl orange, and the rationale for this is we want the endpoint to occur at the same pH at equivalence point. We want the color change, which is endpoint, to be signified at this equivalence point of about 5. So you want an indicator that has an acidic endpoint that changes color at an acidic pH. Methyl orange is how I remember this. Red, orange, yellow, green, blue. Roy G. Biv, that's the color of the rainbow, right? Methyl orange goes from red, then to orange, and then to yellow. And it starts off red, and then at a pH of about 3.1, it goes to orange, and then at a pH of about 4.4, it goes to yellow. It's sad I still remember this because I'm never ever going to use this in my life, but that's what the HSC, the old HSC especially, made us do. Ask your teacher if you need to memorize pHs of indicators, right? If you don't need to memorize it, I probably wouldn't, unless you go to a competitive selective school. They can ask you, okay? But otherwise, this is the indicator you would use. Any questions? Good. All right. Again, I'm not going to say anything. Don't look at your notes. Look on the screen. And I want you guys to hit the raise hand icon once you've interpreted this graph and you know the strength of the acid base and you've answered all the questions that we go through. First of all, orient yourself. Look at the start. Look at the end. Look at the equivalence point to confirm, and then tell me what indicator. Those are the questions. I'll write the questions for you to help you out. Orient yourself. Look at the start. Look at the end. Look at the equivalence point and tell me what indicator. Once you've got an answer, hit the raise hand icon. Good. We got one person with an answer. Wait till about at least 2 people have got an answer.
What's the orient?
So you're on mute.
Thanks, Akshita. Sorry, I put myself on mute because I hate the sound of eating, so I don't want to just eat while you guys are studying. Mohammed, have you learnt titration at school?
No.
Okay. You should ideally, if you're on mod 6, you should be on titration by now, otherwise your school is going a little too slow. So orient is all about, so in titration, it's a reaction of an acid and base. Right? There's always going to be this burette, which is delivering solution into this conical flask, which is another piece of glassware. Okay, and the burette, you just turn this little dovecock to allow solution from the burette to drain into your conical flask. The question about orientation is that the pH probe is always measuring pH in the conical flask. So you need to ask yourself, is it the acid in the conical flask or is it the base in the conical flask? That's what the orient question is all about, Mohammed. So I guess this lesson will be a little bit hard for you only because you haven't learned titration, but if you watch the previous lesson recordings, get up to pace. Good. Sid, Ethan have got an answer. I'm going to start with Akshita. Akshita, take it away. First of all, orient us. Who's in the conical flask, who's in the burette, and why?
So the base should be in the conical flask and the acid should be in the burette because we see that even without the change, it's relatively high. It's at 14. The pH is at 14. And so automatically I would think that it's a very, very, very strong base because the ionization is 100%.
Good. Again, we can't confirm the ionization is 100%. We're just making a guess there. This is important because in terms of your wording, so one thing I'm teaching is how to actually interpret these graphs. The other thing you should all be working on, how do I word it to get full marks? So I completely agree with you. At volume of acid equals to 0, which is in the conical flask, there is a very high pH, which is informing you there is a base in the conical flask. 4 marks so far. The way I'd word it in an exam is I'd say the pH titration curve starts at a pH of 14. As this is a high pH, it may indicate that the degree of ionization of the base is 100%. The starting high indicates the degree of ionization of the base is 100%, which would result in a large concentration of hydroxide ions, and thus the high pH observed. Do you see how I didn't make any definitive statements? I didn't say the degree of ionization is 100%, I just said it indicates it could be or maybe. Okay, it's just all about wording. Be very careful in science about using very definitive terms unless you know it's a fact. Next, Rithania, look at the end. We've oriented ourselves. We've looked at the start point and made a guess that it's a strong base. What about the end, Rithania, and what about the equivalence point as well?
I would say the end is a high end, so it's a weak acid. And the equivalence point should
Give
be
me an
like,
exam answer. So give me an exam answer. So this whole point, I want an exam answer as to why you think it's a weak acid.
because the pH number is pretty high for an acid, meaning that's a weak acid. So there won't be 100% ionization.
Good. right? That's the one thing I'm looking for. So I want you guys to pick up on the patterns here. I keep talking about degree of ionization for a reason, because if you can't say anything about strength of an acid unless you mention degree of ionization. If you ever in an exam say the pH was high, which indicates a weak acid, you'll lose a mark. That's completely wrong. The only way you can say that is because you're making an educated guess that because it's a weak acid, it doesn't have a significant degree of ionization, and so it must have a high pH. Remember, even this rule, this would fall apart if it was a very, very low concentration of a strong acid. That could also have a high pH. It's just such a low concentration, the pH still seems high, even the degree of ionization is 100%. That's why I'm showing you we're not making definitive statements, we're just making a guess. And we're assuming it's at a reasonable concentration. Very good. What indicator, actually, we haven't even spoken about equivalence points. Sid, your turn. Can you justify the equivalence point in an exam answer format?
Since it's a weak acid, strong base titration, the weak acid forms a weak conjugate base, and the strong base forms a weak, very weak to neutral acid. So the reaction forms a basic salt, and which is around like 9 pH. 9. Yeah.
Good. I like that answer, right? So, in essence, you'd say, as this is a weak acid strong base titration, the salt would be composed of a conjugate of the weak acid ion, which would be weakly basic. As the salt is basic, equivalence point would occur at approximately pH greater than 7, as seen in the graph bracket pH 9. Very good answer, Sid. Ethan, what indicator would we use? Any ideas? It's written there, but do you know what color change we observe and what the pH range is?
For the phenolphthalein indicator, it starts from like transparent, and then once the equivalent point of around 9 is reached, it turns to pink.
Good. I'm happy with that. pH 9. Fine. If your school doesn't want you to remember numbers, fine to say 9. If your school cares about you memorizing the numbers, which is a bit silly because it's not useful at all, you can Google search the stuff. You should know the exact range. Good. Would have already seen this, but can someone go through this one as well? So orient, start, end, equivalence point, and then think about what indicator we might use, or tell me why there would be a difficulty with using an indicator. So I'll help you out here. There's no suitable indicator for this titration. It's your job to tell me why at the very end. So for now, hit the raise hand icon once you've explained the orientation, the start, the end, and the equivalence point. Okay? I'll be right back. Okay, I hope you all got an answer for this. So now, let's go to Ethan. Can you try taking us through the entire answer?
Wait. The base should be in the conical flask, and the acid should be in the burette.
Good.
Yeah. As indicated in the graph. From the pH value of 11, it indicates that it's likely to be a weak base because it doesn't ionize to completion. So the pH value is around that. The endpoint is relatively high, so it indicates that it's likely to be a weak acid rather than a strong acid. 11 goes to 100. Yeah.
Keep going. We haven't said anything about the equivalence point.
The equivalence point is 7 because a neutral salt is produced with a weak acid and weak base reaction. But because there isn't a really sharp pH change, by just using an indicator, we cannot visually see that change because that is really small.
Good. I'd agree with you on that. Good. All right. So I think the key things here is make sure you always link strength to degree of ionization before you mention strength and the link to pH. You are all completely fine to just say that pH is 7 as this titration would make a neutral salt. One thing the marker is looking for is this, but if you want to be more detailed, do mention conjugate acid-base pairs, right? So you could say this is due to the fact that the conjugate of a weak base is a weak acid, and the conjugate of a weak acid is a weak base. So this salt would be composed of a mildly basic and mildly acidic ion, which would contribute to overall neutrality. It all depends on how many marks the question is as well. Okay, and you're completely right. You guys see with all the other graphs, there's usually a sharp pH drop at that exact same volume at equivalence point. Whereas here in this graph, there is no sharp drop in the pH titration curve. Since we don't see a sharp drop, the pH is changing very gradually, right? It could be around, what is it here? About maybe 7 point something, all the way to here, it's like 6.9. Whereas in the other graph, the pH drops all the way from 12 to 4 at the volume of equivalence point. So you could use literally any indicator that has an endpoint between 12 and 4. That's reasonable. Whereas in this graph, you need to find an indicator that changes pH between 7 point, what is that? Let's just say 7.3 and 6.9. Very hard to find. Right, very few indicators would be satisfied here, and this is why you'd need to use a pH probe in titration for a weak acid, weak base. Good. Does everyone feel confident or more confident? I guess the only exception is if you haven't learned titration or are new to all of this, it would still be very foreign. But for those of you who've learned the background knowledge, do you feel confident with interpreting and answering pH titration curves, explaining their strength, and providing a suitable indicator? That is every time you get the same exam question. Ethan, question?
So sorry, yeah, I've got a question.
Yeah.
Do we have to use a pH probe every time, or can we just use the indicator?
It wouldn't be suitable to use an indicator for this titration, only because the endpoint, it's very hard to pick an indicator which has an endpoint which will occur exactly at this equivalence point as well. If you can find an indicator that changes exactly between 6.9 and 7.3 or within that range, feel free to. But I don't know an indicator that can do that. That's why you want to use a pH probe. Alternatively, you can also do, you guys will learn this soon, use a conductometric probe, which measures conductivity of the solution. Good. Any other questions at all? Good. All right. Okay. Exam question. This question is actually, I need to fix something. Let me just have a quick read. Yeah. This should be sodium hydroxide. So just cross that out and write sodium hydroxide for me. Good. I'll give you guys about 2-3 minutes. 2 minutes. And I'm going to ask someone for an answer. Okay. There's the only point, Mohammed, I wouldn't expect you to come to an answer to this question yet because you haven't learned titration. Once you watch the previous lesson recordings, it'll make a lot more sense. For now, Mohammed, just focus on trying to understand what titration is. Have a look at some notes. You can quickly just search on the internet as well. And I'll try explaining it while I'm doing this too. Who's close to an answer? Sid, take us through graph 2. Break down the graph. So the way you guys should all be approaching this, breaking down the graph, determining the strength of the acid and base, and seeing which one of the options fit. So Sid, from start to finish, give us an exam answer on graph B and which reaction you think graph B represents.
So graph B starts at a relatively high pH, which indicates
Orient yourself first. So who's in the burette, who's in the conical flask?
Oh, okay. So the acid is in the conical flask, and the base is in the burette.
Good.
So since the pH starts at a relatively high, it indicates partial dissociation. So we can assume that it is a weak acid, and the endpoint is at a very high pH, which indicates 100% ionization. So we can assume that's a strong base. The
Good.
equivalent.
Yeah.
Uh,
Well, one thing I'll say, sorry to cut you in, but I really liked how Sid didn't say any definitive statements, right? That it indicates or it can be assumed, right? And that way you're kind of getting yourself out of making definitive wrong answers. But good, Sid. When you're ready, keep going.
The equivalence point is in the basic pH range. So this is due to the weak acid forming a weak conjugate base, and that forms a basic salt. So an appropriate indicator for this reaction is phenolphthalein.
Good. Very good. Right. And now, which one of the reactions is represented by that graph, Sid?
Number 2, acetic acid. And so
Nice. Very good. Very good. Good job. I think that would be in a full mark answer, right? You've spoken about this at the beginning, you've spoken about the end, you've justified the equivalence point with conjugate acid base pairs, got the right indicator, right? There's nothing more you need to do. Very good. And can I get Akshita? I'd like you to break down graph 1 on the left.
So, when we look at the starting of the graph at volume 0, the pH is 3. So it is assumed that the
Is it pH 3 or 1? Dudley graph.
Isn't it pH 3?
Are we looking at the same graph? This one right here, where the start of the graph pH is.
Oh, are we? Oh, okay, yeah. Yep.
Sid already explained graph 2.
Yep. So pH 1. So we're assuming that it's a strong acid.
Yep. Good. Orient yourself first, but you don't need to write the orientation part in your answer. So I just wanted you all to say that so I knew you were orienting yourself first. But okay, good. So you started here, you've gone start, strong acid. Okay. Why is it a strong acid? Keep going.
Because we can assume that it fully ionizes, so 100% ionization.
Yep, keep going. I want a full exam answer from start to finish.
And then when we look at the end of the graph, it's at pH 12.5, and we can assume that it's also a strong base, because of 100% assuming that it goes to 100% ionization. And we look at the equivalence point. The equivalence point is 7, and we know that when a strong acid and a strong base react, it produces a neutral salt. And from the reactions, I think it's the hydrochloric acid and the sodium hydroxide, because hydrochloric acid is a strong acid and sodium hydroxide is a strong base. And an indicator would be bromothymol blue, because it detects pHs of 6.2 to 7.6.
Very good. Very good. Good answer. See? So now you guys we're going from breaking things down at a very fragmented pace to putting it all together to an exam answer. Very good. Very good. I think both of you, for Sid and actually, I think one tiny tweak is, you can say, we can assume it's a strong acid, it's a strong base. We can also just say this indicates it may be a strong acid, just with wording. But no, otherwise, I would give both of you full marks for that answer. Very good. Good job. I think we're all confident with conjugate acid base titration curves. Here's another exam question, but do that in your own time. Now, we'll have a break first because we've hit the hour mark. But we'll run through conductometric curves after our break. So all we have now is conductometric titration curves and buffers, and hopefully we can start module 7. I think mod 7 is one of my more interesting modules. All of them are interesting. They're very chemistry application based, but mod 7 is just the whole different side of chemistry. Actually, the question.
Yeah, it was just a question from school. Is
Yeah.
it okay if I can ask in the break?
Yeah, sure.
Or-
Or alternatively, put the question up during the break, and then after the break, we'll go through it together if it's an exam question. Is that
It's
all right?
not an exam question. It's just like a quick.
Sure. All right. Yeah. So, okay, everyone take your break now, and we'll recap at about 5:20-ish. Okay. Rakshita, what's your question?
So we were doing a worksheet, and there was this compound, and the chemical formula was K2HPO4, and our teacher said that it was potassium biphosphate, and I searched it up, and it said dipotassium phosphate, and then the answer said that it was potassium hydrogen phosphate, and I was like confused on what it actually was.
Okay, I guess this just comes down to naming ionic compounds, right? When you're naming ionic compounds, for example, it's just to help you out, MgCO2, what do you call this?
Magnesium chloride.
Good. You don't call it magnesium dichloride, do you? And it's
No.
the same thing. When something has if something is a covalent molecule, then you do have to state the name or the prefix if there is two of that. For example, CO2 is carbon dioxide. We don't state the prefix if there's just one of the first element. So carbon, even though there's one, we don't say it's monocarbon dioxide, we say carbon dioxide. But with ionic compounds, you never state the number here. You never call it dipotassium. That's straight away rings alarm bells in my head because you're naming it like a covalent compound. But that's not right. It should literally just be, first of all, this is also, no, this is right because the hydrogen phosphate ion would have a valency of 2 minus. Yeah, I would call it potassium hydrogen phosphate. That would be the name of that compound. Not biphosphate. I don't know where bi is coming from because we never call something, we don't call it carbon dioxide. It's di according to IUPAC nomenclature. Okay. The other thing to note though is that there are other household names for compounds. For example, acetate or acetic acid is technically not the proper IUPAC name, it's ethanoic acid, but that's usually for polyatomic ions. We have multiple names for them. For this, I would just call it potassium hydrogen phosphate.
Cool. Thank
Good.
you.
No worries. All right, we'll recap at about 5:21. All right. Good. See you guys soon. Okay, when we're all back, make the raise hand icon. I know it's exam time right now. Is anyone doing anything outside of HSC studying? Could be sport, something new you're trying to learn, get better at.
Yeah, I do cadets at my school.
Nice, very cool. Yeah, I think it. What is cadets? Is it what does it entail, Sid?
So like every week, so it's kind of like a place where you could like develop your leadership like skills. So like you join, go after school, and you're running the activities for like the younger students in like doing like activities like field craft, camouflage, navigation, stuff like that. And then we go on like camps as well. Yeah.
Yeah, nice, nice. I think one thing that looks really good, especially in uni applications, is people who've done I think it's the Duke of Edinburgh. And also, yeah, doing cadets and doing some other form of leadership activities. It's really cool. It's good to do because it shows that you're not just focused on one thing and you're able to balance and time manage and organize yourself. It looks really good, even when you're applying for jobs as an adult, if you have multiple other cool things. I think one thing I want you guys to all work on, you don't have to work on it now, but until you get to my age, try doing 2 or 3 really cool things in your life that you can talk about or you're proud of, outside of just your career or your studies. It'll make you a more well-rounded person versus someone who just studies and studies and studies, which I see a lot of people doing that, especially in those academic rigorous courses like engineering, law, medicine. Yeah, try not to make it your entire identity. Good. All right, let's go to conductometric curves. Conductometric curves, they're important to know. They're more often asked in trials as well, but they're very similar once you understand pH titration curves. Okay, you don't need to know them in as much depth, and there are some conductometric graphs such as this one here which just don't make sense and you will never be asked to explain these kinds of graphs, but as long as you can identify the strength of the acid, it's kind of like pattern recognition. Okay, so let me start by teaching you the principles of interpreting a conductometric graph. It's very similar to a pH titration graph in terms of orientation, right? The conductometric probe again is always in the conical flask, so that gives you a bit of information. Okay, have this time, I think you can all appreciate, doesn't matter if it's an acid or it doesn't matter if it's a base, we end up at a higher conductance. So you can't just look at the starting point and go, oh, because it's a high conductance, it must be a base. The way to orient yourself now is just to look at the x-axis, right? What's being added in increasing amounts and understanding, well, that must come from the burette, because a burette delivers variable volumes of solution. The conical flask holds a fixed volume of solution. Okay. The next important application point is that the hydrogen and hydroxide ion have very high conductivity, whereas water and other ions, like the sodium ion and other salt ions, have a lower conductivity. Okay, and you can kind of apply the same principles as you did with pH titration curves, where if there's a lot of hydronium ions, that could possibly indicate a high degree of ionization, and thus a strong acid. Or if you have a lot of hydroxide ions, and it creates a high degree of ionization, strong base. Okay, so key points here: hydronium, hydroxide, high conductivity; metal ions, lower conductivity; water, no conductivity technically, right? Good. All right, let's start by interpreting this graph here. Okay, so we're going to apply the same principles. Let's orient ourselves, and I think I've already done that for you. when you orient yourself, you'll appreciate the base must be in the burette, the acid must be in the conical flask, and the probe is in the acid. So let's start with Ruthania. Ruthania, you see the conductance is initially very high. Initially, we have a very high conductivity. What does that tell you about the number of hydrogen ions that are present in this acid, Ruthania?
It would also be high.
Good. So you have a high concentration of hydronium ions. And what can you thus tell me about degree of ionization and the strength of the acid, Ruthania?
It would be high as well, so high ionization.
Good. Strong acid. Good. Let's look at the end very briefly. It also ends at a very high conductivity. And we know now this is due to the addition of excess base, because at this point here, we've added a lot of base, and that should have reacted with and now become the excess reagent. So there's a high conductivity. Sid, what can you tell me about the strength of the base?
Not is it a I can't wait. So the conductance, is it both applying to hydronium and hydroxide?
Both of them, exactly. Right. So this is what I'm saying. It doesn't matter if it's a hydrogen or hydroxide ion. This is why orienting yourself is important again by looking here, because this is the only cue that will tell you who's in the burette and who's in the conical flask. The reason we know this is the base on the right-hand side, Sid, is because the base is being added from the burette. Okay, and after this point at the end of the graph, that would be when excess base is present in the conical flask and all the acid has been reacted. Does that make sense? Good. Now, Ethan, what do you think this point here is? The point of lowest conductivity.
Is it called the equivalence point again?
Good, right? So the point of lowest conductivity is the equivalence point, and you can rationalize it because at this point there is no hydronium, there is no hydroxide, because all the acid has reacted with all the base exactly. That is what titration is. It's when all the acid has reacted with all the base, there is no more acid and base. The only thing that is present in the solution now are the products of neutralization, which are the salt and water. Mohammed, any idea why the conductance is not 0? Why is the conductance still a value above 0? Any idea, Mohammed? Why is the conductance here?
Because they were both strong base and strong acid. Is that why?
Not quite, because remember at this point, at equivalence point, the definition of equivalence point is all the acid, Mohammed, has reacted with all the base. There is no more acid, there's no more base. The only thing present is the salt and water. Good. So which one is contributing to a slight conductance above 0?
The salt.
Good. Yeah. So that's what I want you all to understand. The reason why the conductance is not at 0 is because there's still some salt present, but it has markedly lower conductivity than the acid and the base. Quite easy to understand, right? Any questions?
No. That is making sense.
Good. Very good. Yeah. This is definitely hard content, especially when you haven't even done titration and you're looking at how to interpret a graph of a reaction which you're still learning. So it's all fine. When you watch the recordings, it'll make more sense. Let's now move on to Rithania. Take it. Actually, we'll come back to this one, Rithania. Do this one again. What is going on here? I'm not going to say anything. Actually, Rithania may have already answered. Ethan. Actually, Ethan's already answered. Everyone's been answering. So very good. Rithania, take it away from start to finish. What is the strength of the acid and base? Don't use this here as your guide because it might be wrong. Whenever you're ready, Ruthenia, take it away.
Okay, so I would say the conductance is quite low, so I would say it would be a weak acid.
First of all,
So
always orient yourself just because it's your first time doing these questions. So who's in the burette, who's in the conical flask?
the base is in the conical flask and the acids in the burette.
Ethan, do you agree? Bases in the conical flask, acids in the burette?
I think the acid is in the conical flask because they said that the ml of strong base, like
Good.
so that's variable.
Good, right? And a
Yeah.
burette delivers variable quantities of solution, right? So the base, I agree with Ethan, is in the burette, very good. And the acid is in the conical flask. Does that make sense, Ruthenia? You can't have a variable amount of base if it's sitting in the conical flask. You can't change, unless you're Harry Potter, you can't change the volume of that solution in the conical flask, right? Good, good. No magic here, only chemistry. Keep going, Ruthenia.
Yeah, so the conductance is high, relatively low at starting point. So I would say it would be a weak acid, and there'll be a less than 100% ionization.
Good.
And then the end point is quite high, so I would say that it would be a strong base, and there'll be around 100% of ionization.
Good. Always link it back to conductance, right? So when you say high, just here, just add high conductance, and here add relatively low conductance. Does that make sense? Or you could say conductivity. Conductivity would be the more correct word to use. Conductance, resistance, those are terms of physics. Just mentioned initially, there's a low conductivity. Finally, there is a higher conductivity. Okay, good. Conductivity. Good. Now, the thing you'll need to appreciate here is you cannot determine anything about the pH of the salt, unlike in a pH titration curve. So it's actually a bit easier. I don't know why the line is here, and I get asked this every year by students. Why is the equivalence point listed in the in-focus textbook here when the lowest point of conductivity is here? My answer is I've seen multiple graphs which also have it here. I don't know why that textbook has it there. For you guys, you should just put the equivalence point at the lowest point of the graph, right? Because at the lowest point of the graph is where you should have no acid, no base. It should only be your salt ions and water. At this point here, you should have accumulated some excess OH minus ions, which increase conductivity. So the line, I think, should technically be there. I've not gotten any consensus from anyone else, but that's what it should be. Good. Does that make sense? So this is an example of a graph that's starting a bit lower and ending a little bit higher. And again, you see this slight curve only because with weak acids, there is more of a gradual change and a plateau in conductivity faster than a continual sharp decline. But otherwise, it makes sense because if you have that continual sharp decline for a particular volume, you can see for a weak acid compared to its strong counterpart, since it curves down like this, it's got a lower conductance than the same volume with a strong acid, which would be a straight line. So it looks a little bit curved. If you are to draw a conductometric graph, you should get full marks for including a straight line as well. You shouldn't lose marks for making it straight. But this is just explaining why it's slightly curved in your textbooks. Good. So again, like I said, for conductometric curves, the most important thing is identifying the graph. Most exam questions simply give you a graph and they ask you which of the following graphs represents the equation, etc. Okay, so you rarely will be drawing your own graphs. Good. This one here. This one I want you guys to think about what this represents. And talk about a very important point in this graph that you might get asked in trials, probably not the HSC. When you get an answer, hit the raise hand icon. Anyone got an answer yet? What does this graph look like? So I'm trying to write the most appropriate equation to show you and explain a very important part of this graph. Good, Daniel's got an answer. Okay, finally found an equation to really show you what's going on here. All right, so Ruthania's already answered this. I'm going to give it to Ethan. Actually, Sita, explain this conductometric graph.
So to orient the graph, I think the acid is in the burette, and the acid's in the conical flask, and the base is in the burette. And looking at the initial when the volume is at 0, we can see that the conductance is relatively high. So that means complete ionization occurs because of the a large presence of H plus ions. And then we see at the end of the graph.
Pause. What does that tell you about the strength? You haven't linked it to the strength, remember?
Oh, that it's a strong acid.
Good. Yeah, always think of what you're expanding towards. Good. Yeah.
And then at the end of the graph, the conductance is relatively less, and so that means that there's less OH ions present, meaning that it would be a weaker base. And the equivalence point is present, and
not much else you can say. You can just,
Yeah.
equivalent point is the intersection of those two lines. Yeah, you won't be required to justify why it's equivalence point. But here's my next question to you. Why does the graph look more or less horizontal rather than going up even slightly? Right? Because we'd expect that when we had more and more weak base, the conductivity should slightly go up, right? Because at this point, there's just salt and water. And then when we add more and more weak base, surely we're increasing the hydroxide ion concentration, which should increase conductivity. Why does it look very plateau or close to being plateau? That's my question to you. And I want you to use the two reactions that I've written to explain why that is the case. I'm going to give you guys a minute to think about this. If you can explain it to me, you're doing really well. Okay. Hit the raise hand icon once you've got an answer. Get some water. Take it away, Sid.
So after it's past the equivalence point at its lowest conductivity, all the acid has completely reacted. So as more weak base is added, there's an excess base, and which ionizes with the water to give ammonium chloride and hydroxide. Since the conjugate acid of ammonia is ammonium, due to Le Chatelier's principle, it increases the amount of ammonium, so you would want to decrease it. So then it reverses. So it goes in the equilibrium shifts to the left. So more water is produced.
Good, you got it, but we need to work on the fine-tuning explanation, which is we form a buffer. That's essentially what's happening. The reason why the conductance is not changing is due to this fact, and we'll talk about it, right? So what's happening here is, first of all, you need to understand what species is what in our little example. So in our example, HA represents, I'm going to write about this stuff that I wrote, do it in purple. HA is a strong acid. Okay, in our example of a weak base, we're talking about ammonia. So those are our examples in sort of thought experiment, right? So what happens is, from the neutralization reaction, we form ammonium ion. We form a decent quantity of it because it's the ion that comprises of the salt, right? Eventually what happens is, at this equivalence point here, just as Sid mentioned, there is no more HA. There's in fact no more NH3 as well, because that's what equivalence point is. All that's left is NH4 plus. And then when we add more ammonia, everyone, we're adding this ion here. Okay, and when we add this ion here, NH3, we now start to get similar quantities of NH3 and the conjugate base NH4 plus. Right? And what we usually say is, when we add more base, the conductivity should increase. But what happens is, when you add more base, because you have similar quantities of a base and its conjugate ion, you form a buffer, which must obey Le Chatelier's principle. This is the other conjugate ion. I'm going to highlight it because these are the exact same. And so down here, when we're adding more and more weak base NH3, just as Sid said, according to Le Chatelier's principle, we want to decrease the concentration of NH3, right? And so we're going to shift the NH3 and dissipate it. So what's happening here is, every time more and more NH3 is being added, the equilibrium actually shifts to the right to use up the NH3 and decrease it. And that minimizes the increase in pH that we would expect from this gradient M1 to this gradient M2. Okay, so that is what is happening here in this reaction. We're forming a buffer that's resisting the further addition of weak base by dissipating it and using it up and preventing that increase in conductance. Question, Sid?
Why isn't the first reaction not a neutralization reaction?
Why is the first reaction not a neutralization reaction? It would be a neutralization reaction, Sid. This base here would be slightly basic. That would combine with this ion and it would neutralize. It's just, I've written it in such a way that it kind of doesn't look like one. That's because I've used the letter A, right? If I put, for example, HCl, that would have been a neutralization reaction, right? Because what we'd expect is HCl plus NH3 would give us NH4 plus and Cl minus. And that's technically a neutralization reaction. And in non-gas, in gaseous state, this would combine as such, like this. Yeah.
But doesn't like all neutralization reactions form a salt and water?
Good point. You're right. All neutralization reactions should have the net ionic equation of forming a salt, or at least of forming water. You're right. They should form water, but this technically is still neutralization because there is a proton transfer going on. Because according to Bronson-Lowry theory, the only definition of neutralization is a proton transfer reaction, right? You don't have to form water. So I would still count this as a neutralization, especially the HCl NH3 reaction. That is still neutralization. Yeah, it's just we don't make a neutral salt because you know about conjugate acid-base pairs. Does that make sense? So strictly according to Bronson-Lowry, the reaction above and the blue reaction I've written are neutralization reactions, but you're right, they don't form the conventional water that should form in 99% of reactions.
Okay, yeah.
Good. Anyone have any other questions? Sorry, that's why I spent so long trying to write an equation, because I wanted to show you guys an equation which would explain this phenomena. This is, again, this is not high yield. Right? The only reason I'm showing it to you is if it does come up in a trial paper, you understand where to think and how to think. Okay, good. All right. With a weak acid, strong base titration, wait a moment, it should be weak acid, strong base. This should be weak acid, weak base, everyone. So please change that in your notes. Weak acid, weak base, not weak acid, strong base. Okay. And all I want you to remember for a weak acid, weak base titration is the graph looks like this. You will not be required, according to the HSC syllabus, to explain why the graph looks like this. And it doesn't make sense using our HSC level of knowledge. Okay, because the lowest point of conductivity is actually not the equivalence point. The equivalence point is up here. Okay, and this is one of the few times in chemistry where for the current set of knowledge that we have, you kind of just have to remember this graph, right? As extension knowledge, this is what a weak acid, weak base conductometric curve looks like. If you want to, go have a read as to why it is the case, but it's not within the scope of year 12. Okay, and it requires to understand a little bit more chem. Good. So this is a rare time I'm telling you, please just memorize this, what the shape of the graph looks like and where the equivalence point is. It's not explained in InFocus, not explained in your 12 textbooks as well. So just remember it. And moreover, remember the principles you learned on how to break down a conductometric graph. Okay, the most common graph you'll see is this one. Every single trial question I've seen uses this graph, or let's use this graph here. Good. Let me see if I've picked an exam question. I've got one for you. Yeah, here you go. Hit the raise hand icon once you've got an answer. Good. Tony's got an answer. Who else has got an answer? Good. All right, Ethan, what's your answer and why?
My answer is B. Yeah.
Why did you cancel A out?
I cancel A and D out because there can't be like a zero conductivity in A, so I cross it out.
Good. Yeah. So it always has to be above zero conductivity. The only time you have zero conductivity is when there's pure water, distilled water. So A and D are completely out. What about C?
I was just thinking, like, when I look at C, why is it not like decreasing than increasing? So yeah, I thought B is like more of a reasonable answer.
Yeah, it looks most. So basically, the way I'd answer this would go: this is a strong acid. This is a strong base. What do I know the graph should look like? I know it should look like this. Which one looks the most like that? B. Right. The reason this one doesn't make sense for C is as you are adding or using up acid, because who cares what the volume of titration is? Doesn't matter if it's acid or base. It's a strong ion. As you're reacting, you're decreasing the concentration of hydronium, or you're decreasing the concentration of hydroxide. Why is the conductivity going up? Right? Good. Do this question in your own time. This is a really good question. You can do it in your own time as well. Maybe just this one here, just to test your conductometric. And after this, we'll talk about buffers. And you've got an answer to the raise hand icon. Good. Britannia's got an answer. Anyone else? Good. Actually, to take it away, what do you think the answer is?
I think it's C.
Okay. Why do you think it's C?
Because acidic, well, when I was looking at the graph, acidic acid has a low conductivity, and so out of all of them, like C had the least amount of conductivity, and then sodium hydroxide has a relatively high conductivity, and so I thought C.
Okay. Okay, I like the rationale, and what you said makes sense. The only thing that we haven't, so always go through it in order, right? Which is, first of all, orient yourself. And the difficult thing about orienting yourself is in the above two graphs, since the conductivity is starting high, it must be that NaOH is in the conical flask, and the acetic acid is in the burette, right? And in the bottom two examples, since it's starting low, it must be that the acetic acid is now in the conical flask, and the NaOH is in the burette. So you explain, so we've oriented ourselves, you explained the start, you explained the end, but did you explain why the equivalence point is there, Akshita? What must be true about equivalence point? It must always be the highest or lowest point on the graph.
Lowest point.
Is it the lowest point on graph C?
No.
That is the reason why C does not make sense. Okay, so C is not the answer. What about option D? In option D, the equivalence point is the highest point on the graph, which also doesn't make sense with the principle that I told you, which is that the H plus and OH minus and H plus and OH minus ion have significantly higher conductivity than the salt ion. So now we're left with A and B. What do you think between A and B? Nathaniel, what do you think? Actually, I've already asked you, Nathaniel. Let's go to Sid. What do you think?
So B looks like it is a strong acid, strong base titration, mainly because of the high conductivity on both ends.
Very good.
A
right? And it's not even the both ends, it's the gradient as well you should all consider. Because a graph like this would eventually have the same higher conductivity, but you can see the gradients here are completely different, right? You're right. Since there's the same gradient of increase and gradient of decrease, both must be of similar strength. That's what it's telling you. And that's not true with sodium hydroxide and acetic acid. That takes B out of the equation. Does this make sense? Yes, because remember I told you, I explained to you why with a weak acid or weak base, the conductivity doesn't increase much past the equivalence point. That's because we form some degree of buffer which prevents further increase or ionization of the acid. What happens here is we form an acetic acid buffer. That's literally what happens. Plus H2O gives us CH3, COO minus, plus H3O plus, right? And any further increase in addition of acetic acid will cause the entire equilibrium to shift this way and decrease that acetic acid. And that will prevent the pH from going down. This is not a pH graph, so it will prevent the conductance from going up. Okay, it should not go down. That was my mistake. It should go up. Okay, so good. I would say A is the best answer. Who got A as their answer? Good, good. Right? Do you see why exam questions help so much? If you guys just learnt the content and we moved on, you'd come to exam questions and you'd think, wait, I swear I knew this, but I'm still not getting it. It's because once you start doing exam questions, you start realizing what's important. And I think the learning point from this question was the equivalence point is always the lowest point in the graph, unless it's this wonky graph that I have never ever seen in an exam question. If you see it, just pick this as your equivalence point, okay? But all other graphs, the equivalence point is the lowest. You can see from the few questions you've seen, they don't ask the rare weak acid, weak base conductometric graph questions. Okay. Good. Model the neutralizations of a strong acid, weak base using a variety of media. Look, I'm not even going to go through this dot point. This is a very school kind of dot point. Just looking at images, looking at digital models, the internet. The only thing I will talk about are models and pros and cons, and they're all written here as well. The main cons are that they're oversimplified, not to scale, they're static, they may not have a key, and the main pro of a model, it's a visual representation of a scientific phenomenon. So it's educational and it simplifies the concept, makes it easy to understand. Okay, forget about all that, those questions. Let's do we'll talk about buffers very shortly. Maybe before we talk about buffers, you do all these questions in your own time as well, guys. The harder titration questions. They're really good questions for you to do. I would make sure I did every question in this booklet. They're challenging. Yeah. I specifically picked questions that I thought were harder band 6 questions. Skip this, this. We've already done this, by the way, even though I'm skipping it, right? KA, pKa, conduct chemical analysis of household substances. The only thing you should probably look at in your own textbook is a stop point about acid-base analysis techniques used by the Australian and Torres Strait Islander peoples. So digital probes and instruments are the pH and conductometric graphs, right? In terms of industry, we use titration in determining the concentration of ethanol in wine or the acid content in wine. I'm sure a lot of you have done titrations or seen questions of titrating aspirin. So if you just mention those two examples, you'll be set. But do look at your InFocus textbook about the use of pH analysis techniques by Indigenous people. I'm no means an expert on that. There's a reason I kept that out, because you just read that knowledge and just remember it. Okay, good. Skip all this, skip all this. Good. Let's talk about buffers. Can you guys hit the raise hand icon? Who's learnt buffers at school or taught themselves buffers? So I know how fast to go through this. Okay. So what does it mean to buffer something? Ethan, maybe take it away. What is a buffer in general?
I haven't really learned it, but like from others' experiment, I kind of get the idea. Is resisting like the change.
What change is it resisting? Well, you're completely right. A buffer is anything that resists change, and you're right. A buffer in chemistry is one that resists changes in pH. Very good. The way it does that is very simple. You already know this. It's Le Chatelier's principle. And the secret is when you have comparable amounts of a weak acid and conjugate base. This is a perfect example to show you, right? Here we've got a weak acid and we've got a weak conjugate base. When we have similar amounts of both of these ions here, this weak acid and weak conjugate base, we form an equilibrium, because that's a definition of a weak acid. It forms an equilibrium which must obey Le Chatelier's principle. Now, if you think about how it's going to resist changes in pH, well, Ruthenia, what would happen if I added hydronium ions to this equilibrium? So the reason I'm writing S, O, and D, for those you might have forgotten or not seen this before, the S is always a stimulus according to Le Chatelier's principle. The O is the opposite to the stimulus. You literally write the exact opposite to the stimulus. And D is what direction is the equilibrium going to go. So Ruthenia, take it away. What if I add some extra acid into the equilibrium?
Okay, the stimulus would be increasing hydronium ions. Then you want to decrease hydronium ions. So the equilibrium would shift to the left.
Good, we'll shift to the left-hand side, go to this way, right? And when it shifts that way, it's decreasing the concentration of hydronium ions. And as a result, it's minimizing the decrease in pH. So a perfect example, let's imagine this increase in hydronium would drop the pH by 1 unit exactly. Now, according to Le Chatelier's principle, there's a partial counteraction of the change. The pH will increase. Will it increase by 1 unit or less than 1 unit, Sid?
Less than 1 unit.
Good. It's a partial counteraction of change. So as you can see here, the net effect is still a decrease in pH, but by 0.5 units. But because of Le Chatelier's principle, we've minimized the drop from 1 unit to 0.5 units. This is just a random example to show you. Okay, so it's not counteracting changes in pH, it's minimizing changes in pH, minimizing the magnitude of change. Now, as you can imagine, a buffer is most powerful when there are similar quantities of the acid and conjugate base. And they're actually most powerful when there are equal number of moles of acid and equal number of moles of conjugate base. The reason is I want you guys to think about this. Imagine there was a very, very small number of moles of my conjugate base, the hydrogen carbonate ion. If I shift my equilibrium to the left, I could very easily deplete this ion. And the second this ion goes, the entire buffer breaks down. And so we wouldn't say that's a strong buffer. A buffer that's strong can resist changes in pH across a large range. And so they work best. Buffers work best when there are equimolar amounts of a weak acid and its conjugate weak base. Any questions about how buffers act? Let me just ask you another question. Actually, what would be the effect of adding a base to this buffer here? What would be the effect of adding a base?
And that would mean an increase in hydroxide ions, and then the opposite of that is a decrease in hydroxide ions, and that would mean a shift to the right.
Why are we shifting to the right? There's no hydroxide ions in the equilibrium.
Yeah.
Sid or Mohammed? What would be the effect of adding hydroxide ions, Mohammed, to this equilibrium? According to Le Chatelier's principle. What would be the effect? Sid, can you help Mohammed out? What would be the effect?
So since so the hydroxide ion would react with the hydronium ion to form water. So
Good.
it decreases the amount of hydronium.
Good, right?
Yeah.
So everyone, I want you to remember this. If the species that's being added is not in the equilibrium, you need to ask yourself, is it going to react with something that is in the equilibrium, right? That's the thinking all you should have. So very good job, Sid. Hydronium ion concentration would drop. The opposite of that is an increase in hydronium ion concentration. And as Akshita said, it would shift to the right. But I wanted a clear explanation because you wouldn't get any marks if you didn't mention that part. Good. Now, there's two things you all need to know, which is, first of all, an example of a buffer in a natural system. So what we just explained, according to Le Chatelier's principle, is how a buffer works. So you must explain how a buffer works according to Le Chatelier's principle. Okay, I'm sure you can all do that. But what you need to know is an example of a buffer in a natural system. Now, this is the exact buffer we have in our blood that maintains a pH of 7.35 to 7.45. Okay, I want you all to remember that. This is the buffer in blood that maintains this pH. The reason this is so important, every time I've had so many sick patients that I've had to take care of, and whenever I'm worried that the patient is getting very sick due to an infection, due to rapid blood loss, due to organ dysfunction or kidney failure, one of the first tests I order is a venous blood gas test. And that blood gas test tells me the pH of the blood. And when the pH is outside this range, especially when it's in the acidic range, I get really worried, because what that's telling me is there is some additional acid, like lactic acid, in the blood that's being made because the body is deficient or losing oxygen. That's what happens in a severe heart attack. That's what happens in severe infection. The blood becomes acidic. So this pH range is imprinted in my memory so I can interpret these blood gas tests. Okay, and that tells me at the biochemical level, this equilibrium has stopped working. Okay, 7.35 to 7.45 is a pH maintained by this buffer here in the bloodstream. Okay, very good. It's very interesting because what happens is when someone has acidic blood, one of the first responses they do is they start hyperventilating. And the reason they're doing that is because where does this carbonic acid come from, everyone? It comes from breathing in carbon dioxide that then goes to the lungs, dissolves into aqueous state, and then combines with water to form your carbonic acid. So by hyperventilating, what the body is doing is it's removing carbon dioxide gas, which is going to shift this equilibrium to the left-hand side to minimize the drop in CO2 gas. And that's going to decrease CO2 aqueous. When you decrease the CO2 aqueous concentration, it'll shift this equilibrium to the left. That's going to decrease the carbonic acid concentration. When you decrease this concentration, this shifts to the left, and that drops the hydronium ion concentration in blood and tries to bring the pH back to normal. That is why after a sprint, when you've produced the lactic acid, you also start to breathe fast. You're blowing off the acid as carbon dioxide gas. Very interesting. The body works together with all its organ systems to maintain this range. If you're outside this range, you die. That is the end effect if it stays outside this range. So that's what I'm showing you, how important this buffering system is for life. Good. Any questions about buffers? The last thing I'll say, I know we've run a little bit out of time, but it's just so we can completely finish this module, guys, is that whenever it comes to buffer calculation questions, you all must think, whenever they ask you to calculate the pH of a buffer system, you need to use the Henderson-Hasselbalch equation. We've all seen this before, except those of you who haven't been here in previous lessons, which is pH is pKa plus log 10 concentration of the conjugate base, which is A minus, divided by the acid, which is HA. Right, that's the acid. Okay, and think about what this equation would mean when we have an equimolar concentration of acid and conjugate base. Sid? So if I have a buffer that has an equal concentration of acid, equal concentration of conjugate base, Sid, what would A minus divided by HA equal to?
1.
1. What's log 10 of 1?
10.
0. Okay, so in that case, pH equals to pKa. And that's just to show you a buffer is strongest when there is an equal concentration of an acid and its conjugate base. So this is HA is the acid, so it'd be H2CO3 in this example. A minus would be the HCO3 minus, the conjugate base. And when there's equal concentrations of those two ions, the pH is equal to pK. And mathematically, what that's telling us is that buffer is at its strongest buffering capacity. This is the Henderson-Hasselbalch equation. I'll go through it next week as well in the beginning. But technically, guys, we've finished module 6. Okay. Don't worry, next week I'll take you through 1 or 2 Henderson-Hasselbalch equations, reinforced buffers, and we'll start organic chem. But otherwise, have a read of all this stuff. Do these exam questions. These are all Henderson-Hasselbalch equations. But good job on getting through mod 6. What week are you all at school right now? What week is everyone at?
Week 7.
Week 7, right? So week 7 of term 2, we've already finished mod 6, so we have some ample time to do mod 7 and 8. Good. All right, any questions before we finish up today? Good. All right. Those of you who have a question, stay back, but otherwise, I will see you all next week. And Mohammed, do you mind staying back for a moment as well? So Ethan and Mohammed. Thank you. See you guys next week. Bye, Akshita.
Bye, sir.
Bye, Cynthia. Ethan, you had a question? Let me just stop the recording first. Yep.
Sir,